Welcome to the next lecture on process control analysis and simulation. So, in this lecture we are going to play around with PID gains, and we are going to see like how each has some effect on the control loop behavior. So, we are going to mostly use MATLAB for this particular lecture. So, what we are going to basically see is like we are going to see the effect of PID gains for the steady state error, which is the offset, and the parameters like settling time, rise time and overshoot. So, and finally we are going to look at this table and see like whether we are able to observe all these relationships between whatever, if we increase these values, what will be the effect on offset and what will be the effect on rise time, what will be the effect on settling time and what will be the effect on overshoot. We will switch over to MATLAB and we will see the effects. So, if you could see here, this is the Simulink that we have developed. So, let us just go through this control loop to understand what you have done. So, if you can go to Simulink and find the blocks of step, PID controller, LTI system, you can get all these blocks. And what we are trying to do is like we are having a system. This is a system. System is nothing but 1 by s q plus s square plus 2s plus 1. So, that is what this transfer function says. So, the first one is the numerator, and these actually correspond to the coefficients in the denominator for the powers of s. And then if you could see here, like this is the set point, which is we are trying to give a step input. We wanted to change the value of the controlled variable by a step input, and then we are going to see how the system is behaving. So, basically what we are trying to achieve is a servo response. Basically we are trying to change the set point, and then we are going to see how the output is following the set point, and the input signal we are giving for the set point is nothing but a step input. And this is a PID controller block that is inbuilt inside the MATLAB. So, this is not going to have Kp, Ki and Kd, and we are going to observe that if how the output is going to change. And also like towards the end of this we will use this particular thing which is just going to generate a noise. So, any measurement has some noise. So, we are trying to induce effect of the noise into the output and then see how this controller is going to behave as well. So, that is what we are going to do towards the end of this. So, with that we will just start simulating and seeing the responses. So, if you see here, like I just open the blocks and show how it what are the parameters inside it. Maybe you can, if you have any doubt, you can also go to the website like online MATLAB and then see that there are like good explanations available in the internet, but just let us go through it quickly once. So, step input says like the initial value is 0, so it changes from 0 to the final value 1. So, step time is like at what time I wanted to create the step. For example, let us say I wanted to change the initial value from 0 to 1 after like 5 seconds or 5 steps of simulation. So, that is what we are going to do here. And if you open the PID controller block, you can see here there is a proportional gain, integral gain and the derivative gain, and this is what we have here. And let us forget for now about this filter coefficient. It is the differentiation that we are implementing here. So, let us forget for this for now, and then we are just going to change this PID value Kp, Ki and Kd values and going to see how it is having the response. And also there is a but if you could see here, there is a option here called tune. This will open the MATLAB's PID tuner blocks, which you can use for automatically tuning getting the values of Kp, Ki and Kd. That is, but for now we are not interested in tuning the controller and seeing that. What we are going to do in this lecture is just going to change these values and then see like what are the things that changed to get an understanding of it. It is just like a game that we are going to do now. So, let us now start with and this transfer function block is nothing but as we already discussed, this is the numerator and then this gives the powers of the this is the coefficients of the powers of s in the denominator. And this is summer block. So, this adds this signal with the noise. So, if you could look through this signal, then it just says like what will be the mean of the noise and then what will be the variance of the noise. So, we have put both as 0, which means effectively there is no noise now. So, without noise we are going to simulate first, and this is the scope and this is the multiplexer which will actually show both the signals, both the set point signal and also this particular signal onto the scope. So, let us start simulating. and seeing. So, now just remember the value of proportional gain Kp we have is let us start with a small value. So, 0.1 and Ki value is 0 and Kd value is 0 again. So, we are just going to see how the system behaves. So, now if you could see here, the yellow line shows the set point change, this is how we wanted the output of the process to vary, but what has happened is basically the output has changed from 0, it has increased, but it has some error. See, if you could see here, we want the value of 1 here, but it settles at the value of around say 0.1. So, this is called steady state error. So, at the steady state, after everything, like there is no transients here, so it is maintaining this level, right. So, at the steady state, what is the error I have between whatever value I want and whatever value the control loop, the output of the process is basically. So, that is like there is a constant error now. So, that this is called steady state error. So, steady state error here is nothing but 1 minus 0.1, it is 0.9. And also let us now increase the value of Kp and see what happens. So, basically what we are going to do now is basically increasing the value of Kp, let us say 0.5, and then we are going to see what happened now. So, as you could clearly see, the offset has decreased. So, increasing the Kp is decreasing the offset, also offset is a steady state error. So, that is actually decreasing. It was initially the final value of this control variable was 0.1, now it has become like around 0.35 or something. So, basically the steady state error, the difference between the value we desire and the value we have got has decreased. So, now there are two things we observed, right. One is like increasing the proportional gain has decreased the offset, and also like it has also induced some actually it has, if you could see the previous one, we will compare both things. So, if you could see the point 1 value, and then if you could see now this has crossed like the final value by a very small amount. So, if you could see the final value here, it is around 0.1 or something. So, but here if you could see in the initial starting portion, it has crossed that final point and then decreased, and then it has settled that point. So, this value has also increased. So, this we call as the overshoot. What is overshoot is nothing but what is the increase in this value that it has gone and come down when we comparing to the final value. So, now increasing the proportional gain has actually increased the overshoot. So, now we can we have both the values of Kp in this particular slide. So, this is nothing but what we have simulated for Kp equal to 0.1, and this is what we have simulated for Kp equal to 0.5. So, we will compare both the things. So, first thing we can easily see is like this is the offset here and this is the offset. So, increasing the proportional gain has actually decreased the offset. So, this is some same value around 0.9 approximately, and this is something around 0.6 something, 0.65 or something, maybe lesser than that, but yeah, that is qualitatively what we have to understand is increasing the proportional gain has decreased the offset. Okay. And another thing that we can see here is like if this is the final value, see this is the final value and this has crossed the final value by this particular quantity, this particular value here, and this is the final value where it is settling, and this is the value by which it has crossed initially. So, this is called, this initial peaking is called the value that it peaks is called like it shoots the final value, it goes over it and then comes down. So, this has also increased. See this here the value of overshoot is like very less, very small increase, and here the value of overshoot is very high. So, these two things we can very easily observe from these pictures, and also like if you could see here we can also define another entity called settling time. Settling time is nothing but the time taken for this value to go between the two ranges. For example, like here let us say this is the final 0.5 is the final value. So, to be within 0.2% of this particular value is what we call settling time, and this has like become like somewhere around here, and this is like this is even here you can see like it is going here, and then so like since it is a smaller value, the 2 percentage is also smaller. So basically this is again 2 percentage of the final value here. So this is around 2 percentage of 0.1 and this is like 2 percentage of 0.3 or something. So more or less this is settling like this 2 percentage comes around here. So there might be some effect, but it is not like very appreciable effect as we can see from overshoot or the offset. So this is what we observe on like what happens when we increase the proportional gain. So the main thing that you can carry with and like one more thing you can see is like there is a thing called like from 10% of the final value to 90% of the final value, what is the time taken. So that is called the time to rise, that is the 10% of the final value to the 20% of the final value, how long it takes to go. And if you can see here, this is like a slower thing, right. So from 10% of this to 10% of this may take some time, and this is like too short. So if you can see here, this time is longer than this time. So this when you increase the gain, we can see two things. One is the rise time is decreasing, okay, and offset is decreasing. So these are the two things that we can clearly make out from this, and also we can see another thing is like overshoot is increasing. So these are the observations that we have on increasing the proportional gain, what happens. So you can also like play with different transfer functions and observe that these things are right. And one more thing we talked about, but we didn't observe anything significant, was settling time. Settling time actually did not have any great impact, or we cannot make out anything about settling time. Now the next thing we will go to the integral controller and see like what happens with the integral controller. So coming to the MATLAB again, and we are going to change the integral controller. So let us say we are going to have the integral controller by 0.2. Just we are giving some small value to start with. You can give some other value and see how it behaves. Let us see how it responds now. So the most interesting thing about this one is like there is no steady state error. Basically the value is reaching the set point. So that's the very good thing about integral controllers, and that is the reason why most of the controllers that are used in the process industries are PI controllers, proportional and the integral controller. So integral action is a very good thing to have from the perspective of it eliminates the steady state error. So when we say I wanted to go to say 90 degrees Celsius, if we have just a proportional controller, we may not go to 90 degrees Celsius. We may stay somewhere at 80 degrees Celsius. We can never go to 90 degrees Celsius when we give a step change in the set point, etc. But this integral controller actually solves that problem. It goes to the it reaches 90 degrees Celsius. So now we will try changing the values of integral gain and see like what happens when we change the integral gain. So one thing is, whenever we have an integral controller, it is going to remove the offset or remove the steady state error. So the next question is, okay, what will happen if I change the integral gain, what will be the output? So that's how the output is going to vary. So that's what we are going to see now. So let us take like, okay, we will go to 0.5 and see what happens. Yeah, so basically if you can see here, this is looking different from that. So let us put both these things together in a single page and compare both the values, both the charts. So what I have done is I have put both the figures on the same page so that we can compare them. So this is nothing but Ki is having a value of 0.2, and this is nothing but the Ki is having a value of 0.5, and Kp in both the cases is the same, so it is 0.5. So what are the things that we can see here? First thing is like for this particular first graph, like when Ki was lesser, that time that it went into a particular, say let us say this is 2%, let us assume this is 2%, it went into that quite sooner than this. So if you can draw the same 2% here, because it is the same value, 2% of the final value, and in both the cases the final value is nothing but 1, because it is going to eliminate the steady state error, so there is no offset, so the final value is the same. So within this particular 2% range, this goes faster than this one. So, when you increase the Ki, settling time is actually getting higher. So, it takes longer for me to go and stay within a particular range. So, it takes a longer time to go and stay within this, because here and all it goes outside of this range again. So, here probably somewhere here it goes within this range and stays within there. So, settling time increases when Ki increases, and let us take this one. This is, let us say this is like 10% and this is 90%. So, the time taken to rise from 10% to 90% here is actually longer than here. So, when I increase the Ki, the rise time is decreasing, because here it is faster. See here within 10 seconds it came, but here if you can see here it took more than 10 seconds. So, that's again that's something that we can evidently see from this, and also like see, increasing the Ki values does not have any effect on steady state error. Whenever you have some value for Ki, whenever there is an integral action, steady state error is going to go to 0. So, going to reaching 0, like steady state error reaching 0 has no impact on Ki, because for any value of Ki the steady state error is going to get eliminated. So, that is something that we will not worry much about now. And the other thing that we will see is like we were talking about another thing called how much it shoots over. So, if you could see here it after the final value it has crossed only a very small level. So, here overshoot is very less, like percentage, like after this is the final value. So, how much above the final value this has gone, that is very less here, but here how much above the final value it has gone is very high. So, increasing the Ki actually increases the overshoot value. So, this is something that we can remember. So, these are the responses that we have for a integral gain. Now, next thing we will go again is to do changes for the derivative gain and see what happens. And so, coming to MATLAB again, and let us put some value for derivative gain now, and let us start with 0.1 maybe, but you can put another values. This is just like we are trying to see what happens basically. So, we are not going by any rule or something, we are just going to change the gains and see what is happening, and basically for qualitatively comparing how these different gains behave. So, coming to this, so here we have to compare this with basically what we are basically using is the Kp is the same, Ki is 0.2, and we have added the derivative gain, and this is behaving like this. One thing we can very easily see is like previously we had some in some places it went above this and then came down, but here it is very insignificant, it is not going so much above this final line. But let us do the same kind of exercise, like we will change the Kd again, like derivative gain again, and then see like between what happens when we increase the derivative gain, and we will now choose a different value of derivative gain. We will say probably we will take 0.5 or something. So, now we have put both the pictures in the same place, so we can compare these two. So, in both these cases the Kp and Ki are the same. So, only parameter that we are going to change and experiment is the Kd value, which is the derivative gain. So, here we had derivative gain to be like let us I think we took 0.1, or I think this was simulated with 0.01, and this Kd value was 0.5 or something. So, now it's just a qualitative comparison. So, you can take any smaller value of Kd here and any bigger value of Kd here. So, we can compare these two qualitatively, like what happens exactly. So, these values do not really matter for this exercise for now. What we are concerned more about is what will happen when we change the Kd, when we increase the Kd, what is the effect it is going to have on the control response or the performance of the control loop. So, what we can observe here is the time taken to rise from 10% to 90 here, 10% to 90 somewhere here is fairly the same. It is not, it might be little different, but it is fairly the same. So, we cannot significantly see any difference between these two values. So, the rise time value, it is not going to change much, it is approximately equal, and but if you can see here the settling time is like this has like more kind of like goes ups and downs more, right. So, let us take some value like if this is 2%, within this is the 2% range and this is the 2% range, this actually goes within the 2% range somewhere early year, right, or somewhere early even year, but this goes within the 2% range somewhere later year. So, basically you can see that the settling time actually decreases when you increase the KD value, okay. So, settling time actually decreases when you increase the KD value, and also you can see here the value of how much like after the final value is here again the final value is here again the set point value, because we have an integral controller, but even without integral controller, even with the proportional and derivative controller, you can observe all these things, which is an exercise for you. You can just put k equal to 0 and then you can observe what happens when KD is increasing when you fix some KP value. So, now if you could see here, here there is a it goes above the set point by some value and then it decreases, right. So, but here it has very negligible, probably does not even go above and then comes down, but maybe it goes a very small amount. So, we can see that the overshoot also, value of overshoot decreases, the value above by which it goes over the final value and then comes down is decreasing when I increase the KD. So, and the steady state error value, that is offset, it is not going to have any effect. So, since see this final whenever you have an integral controller, the offset is 0. So, that is why it is not going to affect anything. Even with the proportional and derivative controller without integrating action, when you set Ki equal to 0 and use only Kp and Kd, when you do this exercise, you will see that the final offset steady state error value does not really depend on the Kd. So, here there is no change. So, let us put everything in a table. We saw the table, and then so this is the table that we are putting it everything together. This is the control equation, which says that the value of the output of the controller is nothing but Kp into the error, which is the proportional part of the controller, and Ki into integral E dt, which is the integral part of the controller, and Kd into d by dt, which is the derivative part of the controller. And we also saw that the MATLAB did not use this exact representation, it had used some n and that then, but that we told like we will forget for now. So, and this is the bias that we initially start the system with. So, this and we have seen that proportional controller, when we increase the gain of the proportional controller, whenever Kp increases, offset decreases, rise time decreases, settling time does not change appreciably, and overshoot also increases, and when you increase the integral Ki gain, integral gain, then offset is eliminated. Not only increasing the Ki, even when you have a small Ki, the offset will be eliminated, and the rise time is decreasing, settling time increases and overshoot increases. So, derivative again offset does not change, and if you increase the K value of Kd, rise time does not change appreciably, and settling time decreases and overshoot decreases. So, with this knowledge, so this knowledge will be very useful. So, if you can have this within your mind, like then actually it will be very helpful when you are going to the when you are looking at the response of the controllers and then saying what is the parameter that I have to tweak to get a better response, what I expected. So, there is some very basic thing that you have to remember, maybe not the entire thing. If you remember the entire thing, that is very good, but if you not, at least very basic thing that you have to remember is increasing the, whenever you have an integral action, there will be no offset. Integral controller removing the offset is something that we have to remember, that and also one more thing about derivative controller is, if you increase the derivative gain, then what happens is that the value of overshoot decreases and the settling time also decreases. So, that is what you have to remember, and then if you want to decrease the time to rise, then proportional, if you just increase the proportional gain, the rise time also decreases. In the next lecture, what we are going to do basically is like go through some formal methodologies, like how to get these values of Kp, Ka and Kd. So, today we have just qualitatively seen through these values, but there are certain rules how to get this Kp, Ka, Kd. Actually, there are a lot of rules based on it's a basically several people have proposed several methods. So, we will just go through some very standard methods, and then we will see how the system responds, and also we will briefly visit the MATLAB's PID tuner block, like how the MATLAB automatically tunes the PID controller itself. It can itself provide the values of Kp, Ka, Kd. So, that will be the topic for the next lecture. Thank you.